Greetings, welcome to today's class. So a quick recap of what we did in the last class. So in the previous class we looked at the factors influencing knocking in spark ignition engines, right. So we discussed what was the influence of various factors like compression ratio, mass of inductor charge, inlet temperature and flame speed, etc., right, on knocking. And we also looked at how knocking is quantified, or anti-knock properties of a fuel are quantified using octane number. And we just started the actual combustion process in compression ignition engines. So if we recall, the main difference in compression ignition engines is that the fuel self ignites. So once the fuel reaches its self ignition temperature. So two points are important, particularly in CI engines, because the fuel is sprayed into the combustion chamber towards the end of the compression stroke. Okay. So the fuel needs to be introduced into the combustion chamber. There are two attributes that are important. First one is atomization of fuel, which essentially involves breaking down the fuel particles into smaller particles and essentially enable the vaporization, so that the fuel vapors mix well with air to form a combustible mixture. Please note that as opposed to a spark ignition engine, the time available for the fuel to combust in a CI engine is typically smaller because of the process by which the fuel introduction takes place, right. So a few more factors where the introduction of a proper air swirl, so that like the fuel is also spread throughout the combustion chamber and not localized, so that we get a near homogeneous mixture of fuel and air in a short interval of time in a compression ignition engine. And in order to prevent the presence of significant amount of unburned fuel in the exhaust, diesel engines are also typically operated with a leaner mixture to avoid unburned hydrocarbons, okay, the engine exhaust. We will look at emissions later on, okay, as we proceed. And to enable the atomization of fuel and also the dispersion of fuel in inside the combustion chamber, the fuel is typically injected at very high pressures in a diesel engine. So we look at these injection systems also later on, okay. So to continue from this point, so today we will start with a discussion on what are the different stages of combustion in CI engines. So once again we would look at a P theta diagram for the combustion in a CI engine close to the top dead center. So this would essentially convey to us, like what happens when the compression stroke is almost getting completed and fuel is introduced into the combustion chamber. So this is the P theta curve for the actual combustion process in a combustion ignition engine. Once again, this is the top dead center. So we can see that this vertical line indicates the phase where the piston is at the top dead center, and we can observe the motoring curve. As we recall, the motoring curve is the trace of the P theta diagram which is obtained when there is no combustion in the cylinder. So the pressure is the peak pressure is reached at the top dead center. So now when the fuel is injected into the combustion chamber in a compression ignition engine, once again there are different phases of combustion. So what are these? So the first phase, which is labeled as 1 here, okay, which takes place from here to here. So this is the point where the fuel is injected, okay, at this point, okay, at the start of the first phase. So the first phase is what is called as a ignition delay period. So we can observe that the first phase lasts between these 2 points. Okay. So, let us say we call these points A and B. Okay. The fuel is injected into the combustion chamber at point A, and we can observe that at point B the pressure in the actual P theta diagram starts to move away from the motoring curve. That means that the fuel has started burning, right. So, A to B is what is called as the ignition delay period. So, how is it defined? This is the time interval between the instant at which the first drop of fuel is injected into the combustion chamber and the instant at which combustion starts. So, this is the definition of the ignition delay period. So, if we look at the diagram, like the instant at which the first drop of fuel is injected into the combustion chamber, we called it as labeled as point A, right, in the point P theta diagram, and point B is the instant at which the combustion process starts. So, those are the 2 instants, right. So, ignition delay is broadly classified into physical delay and chemical delay. So, what comes under physical delay? So, when the fuel is injected into the combustion chamber, right. So, it requires some time to atomize, vaporize, mix with the air and form a combustible fuel air mixture. So, there is some time taken for all these processes to happen. Okay. So, those are the processes that constitute what is called as physical delay. Okay. So, physical delay includes the time taken for the fuel to vaporize, to atomize, vaporize and mix with air. And ultimately rise to the self ignition temperature. Okay. So, that comes under physical delay. So, typically this physical delay can be reduced with higher injection pressures. So, if the injection pressures are higher, like obviously when the fuel is sprayed in, okay, so it is going to essentially atomize and mix faster, okay, because it is going to come as a very fine spray, right. So, with higher injection pressures and also higher cylinder temperatures at the start of injection, right. So, that means that if we increase the compression ratio, right, so then we are going to have higher temperatures towards the end of combustion. So, compression, and that is going to promote better atomization and vaporization, faster ones, right, absolutely. So, what comes under chemical delay? Chemical delay includes the time taken by the chemical reactions required to result in ignition or result in combustion, right. So, that comes under chemical delay. Of course, that depends on the chemical constitution of the fuel, right. Of course, also the operating condition, but it is mainly influenced by the chemical composition of the fuel. Okay. So, those are broadly the physical delay and chemical delay. So, the period AB or the region 1 is the region where there is a significant ignition delay. Okay. So, that is the first phase of the actual combustion process in a compression ignition engine. So, now let us come to the second phase. So, the second phase typically starts from this point B and goes till this point, okay, point C. Let us call this as point C. Okay. So, this is the phase where ignition starts and there is a rapid release of heat energy and the cylinder pressure increases rapidly. Okay. So, we can see that the cylinder pressure increases from point B, okay, moves away from the motoring curve, has a tremendous rate of increase and then the pressure reaches its maximum at point C. Okay. So, the phase of the what we call as phase 2, which is typically referred to as a period of rapid combustion, phase 2, which is what is called as period of rapid combustion, okay, is a phase at which the heat released due to ignition, right, of the fuel, like results in tremendous increase in pressures. Okay. So, this is typically characterized and also like visualized as a period from the end of the ignition delay period, which is point B, okay, to the point of maximum pressure. Okay. So, this is what is typically called as the period of rapid combustion. Okay. So, after the peak pressure is reached, even though fuel is injected into the combustion chamber and even though it ignites and burns, the piston has moved moved away from the top dead center towards the bottom dead center. So, what happens is that although heat energy is now released, it is not sufficiently high to sustain the same increase in pressure. Okay. There is heat energy which is released due to the injection of the fuel and its combustion. However, like the heat energy may not be sufficiently high to increase the pressure. However, the temperature will increase, although the volume has started increasing, okay, there is heat energy which is released, the temperature would still go and increase. Okay. So, that phase is what is called as phase number 3 in this curve. Okay. So, the process 3 takes place from, let us say, C to D, okay, in this curve. Okay. So, what is this phase C to D? C to D is a phase wherein there is drop in pressure, but the fuel is still injected. See, fuel injection takes place in the time interval which is labeled as 5. Okay. So, what is this time interval 5? Okay. So, this 5 is the period over which the fuel is injected into the combustion chamber. Okay. So, you can see that this time period is split into three regions. The first, what we call as region 1, which is the ignition delay, region 2, which is called as period of rapid combustion, and region 3, where the pressure stops decreasing, but still since the fuel is being injected and combusted, we still have temperature increase. Okay. And this phase is what is called as a period of controlled combustion. Okay. So essentially this is characterized as the region from the point of maximum pressure, maximum cylinder pressure, okay, to the point of maximum temperature. Okay. So, that is the period of controlled combustion. And of course, in this process, whatever fuel is injected also vaporizes faster and combusts faster, because there is a lot of already heat energy which has been released, right. So, the combustion process is also faster. Okay. So, if we go back to this P theta diagram, so we can see that the injection process happens from, let us say, point A to D. Okay. So, that is the entire injection process, and at point D the injection stops, and then the unburned fuel is burnt, okay, in the phase what is labeled as phase 4. Okay. So, this phase 4 in this P theta diagram is what is called as the period of after burning. So, in the period of after burning, the unburned fuel burns and it starts from the point of maximum temperature. And unburnt fuel particles are ignited, are combusted in this process. Okay. So, that is what happens in period of afterburning. So, broadly these are the 4 processes that happen during the actual combustion process in a compression ignition engine. Okay. So, the first phase is ignition delay phase, second phase is period of rapid combustion, third phase is period of controlled combustion, and then the period of afterburning, right. Okay. So, this is how the actual combustion process takes place in a compression ignition engine. This is normal combustion. Please note that in a compression ignition engine, the normal combustion is already due to self ignition or auto ignition. Now, the question becomes, like what is abnormal, right, in a compression ignition engine. In a spark ignition engine, when we discussed about knocking, we observed that in spark ignition engines, we have normal combustion if the primary flame front reaches and burns any unburned fuel air mixture, right. We have abnormal combustion or knocking only when a part of the unburned fuel air mixture combusts by itself, and then that results in pressure pulsations. So, then if knocking is associated with self ignition in SI engines, how can we qualify or characterize knocking in CI engines, where anyway the normal combustion process itself is by self ignition. So, let us look at that part. Okay. So, how is abnormal combustion or knocking in CI engines can be characterized? So, as opposed to an SI engine, knocking in CI engines happens at the initial stages itself, okay, of the combustion process. So, what do I mean by that? Let us look at this P theta diagram once again, right. So, if we look at the P theta diagram here, okay. So, consider a scenario where the ignition delay in a compression ignition engine is significantly high. Then what happens? We inject fuel into the combustion chamber, and if the ignition delay were to be high, unburned fuel will start accumulating in the combustion chamber. So, let us say I consider the combustion chamber, okay. I am just drawing a very simple schematic to just discuss this point. Let us say we have the cylinder and piston. Let us neglect all the other components right now, okay, for this discussion, the valves and so on. So, suppose I start injecting fuel, okay, so through the injector, okay, and if the ignition delay were to be high, what will happen? I will have lot of unburned fuel pockets, droplets, which are going to be accumulating in the combustion chamber, because there is a higher time period, right, time interval for them to get spread out. Now, when these unburned fuel particles self ignite, what is going to happen is that it is going to release lot of heat energy, even higher heat energy, which will result in pressure pulses, okay, because each fuel particle itself, if you localize them, it is going to self ignite, and there are going to be some pressure waves, okay, which are going to be generated. If the ignition delay were to be high, what is going to happen is that, like, the number of such self ignitions is going to only increase, right, because we are going to have more amount of unburned fuel in the combustion chamber, and that is going to create some pressure pulses, but at the start of the combustion process, okay. So, if you recall, in the SI engine, the knocking happened close to the peak region, right, because that is how the phenomena was, right. But here knocking, if at all it happens, right, it would occur in the initial stages of combustion, okay, in a CI engine, if it were to happen, okay. So, the main parameter which characterizes or which affects this phenomena of knocking in CI engines is only the ignition delay. So, larger the ignition delay implies larger amount of unburnt fuel particles, injected fuel particles at the commencement of ignition, which would in turn imply higher pressure oscillations, right. So, the pressure pulses, if they are to be significant, would be felt towards the start of the combustion process, okay, in a CI engine. So, the main factor is the ignition delay. So, of course, lowering the ignition delay would lower the chances of knocking in CI engines, okay, lowering the ignition delay would reduce the tendency for knocking. In CI engines. Okay, so that is what happens in CI engines. Okay, so this is the normal combustion and abnormal combustion process in compression ignition engines. Okay, so now once again, how do we characterize this ability of the fuel to prevent knocking in CI engines, right? In SI engines, we quantified the anti-knock characteristics of gasoline using octane number. Similarly, in diesel engines, the ability of the fuel to prevent knocking, right, is quantified by what is called as cetane number. Okay. So, once again it is going to be a ratio of two base fuels that we will take and figure out what is the composition of that mixture will give me the same ignition delay, right, as the diesel fuel which I have been provided. Okay. So, what is the definition? So, it is the percentage by volume of normal cetane chemical composition is C16H34 in a mixture of normal cetane and alpha methyl naphthalene, which is C11H10, okay, which has the same ignition characteristics. So, for diesel this is essentially quantified by the ignition delay of the fuel under consideration when combustion is carried out in a standard engine under a set of standard operating conditions. Okay, so that is the definition of cetane number. Okay, so these are the concepts of combustion process in a CA engine and what is normal and how is knocking characterized in CA engines.